Hello everyone. Today we'll discuss about instruction fine-tuning or instruction tuning, which is one of the key advancements in recent language modeling research, which enables us to easily have a conversation with language models, or simply put, we can chat with language models. First, a quick review. So in previous weeks, we have learned about decoder-based language models. So such models are trained on vast amount of text from the internet using the next word prediction task. As a result of this, these models learn to encode a lot of information about the world. They also have the ability of understanding language to some extent. So these models are very powerful, they're pretty amazing, but we'll see in the upcoming slides that they have some major limitations. One note, these pre-trained language models, they're also known as base models. So I'll be using the term base models throughout the lecture. So whenever I mention base models, it simply refers to pre-trained language models. For example, say we have given the following prompt: what is the national flower of India? We have prompted the language model with this question. Now, what can happen is that the language model can generate the following response: that what is the national animal of India? What is the national bird of India? So this response is nothing but the continuation of the prompt, and this is the result of the next word prediction that is happening after the prompt. So here we see that these are the response contains questions which are like quite common, which we can come across such questions in the web, where we say there's a web page on general knowledge questions about India. There's such questions are very common. However, this is not the desired response, because when we asked this question to the language model, we were expecting the answer. That is, the national flower of India is lotus. This is what was the desired outcome. However, since the language model is just predicting the next word, so the response to a question could be that it may or may not follow the question, might follow the instruction, might not follow the instruction. Because, as I said, it's simply just doing next word prediction at this point. So the key takeaway from this slide is that next word prediction, which is what is governing this response generation, that does not necessarily ensure that the model understands or follows instructions. So the reason we need instruction tuning is that we want to teach the language models how to follow and understand instructions. So multitask learning is another very important paradigm in natural language processing literature. So in classical multitask learning, what we do is we combine multiple tasks, and we train the language model on multiple tasks, with the intention that these models will have a positive influence on each other, and thereby the final outcome will be improved across all the tasks. So here, if we take a look at this example, during training, there are two tasks: sentiment analysis and machine translation. These are two tasks with which we are training the model. So when I say I'm training the model, what I'm doing is I'm simply passing the input-output examples corresponding to these tasks to the language model. There's no explicit notion or explicit information that I'm supplying to the language model, saying that, oh, this example corresponds to sentiment analysis, or this example corresponds to machine translation. No such thing is there. We are just passing the input-output examples, and that is the way we are training the language model using multitask learning. Now, suddenly, during test time, say the language model encounters a new task, which was not there during training, which is, for example, here it is SCOLA, which is the corpus of linguistic acceptability. So what it does is, it's actually a task from the GLUE benchmark. So mainly the task is to classify whether the sentence that I'm supplying, whether it's a grammatical sentence or not. So, but to the language model, this is just a random example, and it has no idea what it is supposed to do with this example. So, as a result, the language model will have no clue and will not generate a legitimate output in this case. Here, a major abstraction is that when I'm training the model, I'm simply passing the examples. I'm not giving the language model any information about the task that I'm solving. Hence, when it is encountering a new task during test time, it is clueless. So again, the takeaway from this slide is that using this approach, the model can only generalize within the training task, and when it encounters a new task during test time, during inference, it struggles with it as it was not encountered during training. So what can be a possible solution? Can we describe these tasks via instructions? So again, in this example, we can see that various NLP tasks can be expressed via natural language instructions. So for sentiment analysis, I can pass the instruction, predict the sentiment of the sentence. This is the instruction that is defining the task, describing the task, instructing the model that what it has to do with the sentence. Action packed thriller, and it predicts the sentiment is positive. Again, for machine translation, I'm explicitly mentioning to the language model that translate the sentence to Hindi. It has been raining continuously for the past few days. So what would be the Hindi translation? पिछले कुछ दिनों से लगातार बारिश हो रही है. So like this, now when I'm training the language model, I'm not only supplying the input and output, I'm also supplying and prepending the instruction along with the input. And the idea is that we want to teach the language model how to understand instructions, because if it can understand instructions, it can generalize across some arbitrary tasks that it has to solve during test time, and since we'll be describing the task, for example, during inference time, we will be when we are now taking the COLA task, we are now describing the new task by an instruction. We are saying, is this sentence grammatical? We are asking the language model, and the language model is able to say that it is not grammatical. So here the change is happening, that now when I'm giving a new task during the test time, I'm describing the task via a natural language instruction. And the idea is that during training time, since we had supplied the language model with similar examples, which demonstrated that how it is supposed to respond to such instructions, now it won't fumble when it suddenly sees a new task during test time, and it would be able to solve it. So this is one of the goals of instruction tuning, where the idea is that it should be able to generalize to new tasks seen during inference time, and these tasks all the tasks will be described via natural language instructions. So with that, we can discuss what is instruction tuning. So to consolidate what all we have spoken till now, so instruction tuning is a fine-tuning technique. We fine-tune the large language model on instruction datasets. Instruction datasets have tasks and examples described by natural language instructions. So these datasets contains examples that demonstrate to the language model that how it should respond to an instruction. So this boosts their ability to understand, reason, and follow instructions. And when it comes across a new unseen task, it becomes better at handling them. So in this slide also we have another example. So this is from the paper Fine-Tuned Language Models as Zero-Shot Learners. Here we can see in the example that during training, we are instruction tuning the language model using a variety of tasks. Common sense reasoning, translation, etc., etc. And for each of these tasks, you see, if we take a look at the translation example, we are first giving the instruction, translate the sentence to Spanish. Then we have the corresponding sentence, which would originally be the input to the language model. The sentence we want to translate. The new office building was built in less than 3 months. And then the target is the translated Spanish sentence. So in instruction tuning, each example is first we have the instruction, the input, and output. These three components. Input is not always mandatory. Sometimes some tasks have input, some do not. But instruction will be there and the target output will be there. One thing is that here the tasks present during training and inference are disjoint. There's no intersection between them. So during inference time, we see how it is performing on a new unseen task, which is in this case natural language inference. So we have the premise which says that at my age, you will probably have learned one lesson. And the hypothesis is it's not certain how many lessons you'll learn by your 30s. And the instruction, so this is originally the input, the premise, and the hypothesis. Now the instruction to the language model is, does the premise entail the hypothesis? So this instruction, we are describing the task we want the language model to perform. And from this, since the language model now has some understanding of what it is supposed to do, how it is supposed to respond to instructions, it responds by saying it is not possible to tell. So we are not sure whether it's an entailment or not. So again, so the key idea over here is, through instruction tuning, we want to teach the language model. We're training the language model to execute tasks based on natural language instructions, such that it can adapt efficiently to new, previously unseen tasks. One more point that I would like to mention over here is, in this week, prompting will also be covered. So there's a distinction between prompting in context learning and instruction tuning. So in instruction tuning, we are fine-tuning the language model. The parameters of the weights of the language model are getting updated. Whereas in prompting or in context learning, no such thing happens. We are not updating any parameters of the language model. So let's discuss about training loss in case of instruction fine-tuning. So say you're visiting Mumbai and you're curious to know what places you can visit over here. So you prompt the language model, can you recommend some places to visit in Mumbai? And the desired target response for the language model is, so here are some great places you can explore in Mumbai, and the list of places. Basically what would happen is that during training, what happens is, at each point the prediction happens one word at a time, based on whatever the input or the instruction which is fed to the language model. Along with it, whatever output has been generated by the language model till this point. For example, this is the input that we had passed to the language model, which is an instruction. For certain tasks, input would also be present. Like the example we saw in the previous slide, the input would also be fed to the language model. Initially, we're feeding the first step, we are feeding the entire instruction and input to the language model. And what the language model would do is, conditioned on this input and instruction, it needs to predict the next word. So it would be predicting the distribution of probability of next word for all the words in the vocabulary. And we know that this is our target word at this point. So here we can use the cross entropy loss across each of the steps, and via that we can train the language model. So this is how it gets updated. Now in the next step, we'll have the instruction input. Along with that, we'll also have this word which was generated by the language model. And with that, the process goes on until the end of sentence token would be encountered, and with that, the generation is complete. Next is a little bit more explanation about training loss for decoder-only models and encoder-decoder models. So in decoder-only models, what happens is we'll be feeding, so I1 to I5 is the instruction or the input that we are feeding to the language model, and O1 to O4 are the output that a language model is generating. So here, these O1, O2, O3, O4, which are colored in red, so these are the actual output that we desire. So this is marked in red because here we are doing teacher forcing. So we are passing the actual output to the language model and not the one which was generated by the language model. This is a difference. So for decoder models, we're feeding the entire thing into the decoder. For encoder-decoder models, we'll be feeding the instruction and the input to the encoder and the rest of the things. And again, due to teacher forcing, we'll be again feeding the actual output to the decoder. And the output would also be generated from the decoder end. So this is just, there's a bit of, there's a difference in architecture between encoder, decoder and decoder models, where there is only decoder component, you'll be feeding everything into the decoder component. Then there is an encoder and decoder component. You feed the input and the instruction to the encoder and you get the output from the decoder. So this is just following the previous lectures. So again, if we just quickly take a look at the formula also, I just described the idea in the previous slide. So here you can see the formulation. So here this is the log likelihood. So this is the conditional probability of generating this token, okay, given all the previously generated tokens and the input that we are given to the model. Okay, and you take a sum of it. Ideally, since this is log likelihood, you will be maximizing this. Similar formulation holds for the encoder-decoder models as well. So another interesting thing in instruction tuning is that there's a lot of diversity in how we can phrase the instruction. Like given a single task, for example, here we have the task of natural language inference. For this task, there are several different ways in which we can describe the task, in which we can provide the instruction to the language model, and all these different ways are helpful for instruction tuning. So say for this task there are 4 different templates or 10 different templates that I can generate. For all of those templates, if I train the language model on that by rephrasing the instructions, we'll see that the model can learn and generalize more effectively. So if I discuss the example in more details, so here we have the premise, we have the hypothesis. The target is whether it's an entailment or not. So the options would be yes or no. So in this template, we have a placeholder for premise and hypothesis and the options. Other than that, the text in red is the instruction describing the task in various different ways. So one way to talk about it is based on the paragraph above, which is the premise, can we conclude that, which is the hypothesis. So this is one way to describe the task. Another way is we give the premise, then we ask, can we infer the following, and then we provide the hypothesis. Another way is read the following and determine if the hypothesis can be inferred from the premise. This is very explicitly we are giving, and we are explicitly providing the premise and hypothesis along with the options. So there are so many ways to describe the same task. And we train the model when we generate the instruction fine-tuning data set. We use all these ideas and train the model on various versions of the instructions for the same task. So here, if I talk about the data set which is present in this slide, it is from the Scaling Instruction Fine-Tuned Language Models paper, which is a very interesting paper. If anybody is interested, please feel free to read the paper. So here, what they have done is they have created this data set, this consisting of 1,836 tasks, which is a huge number of tasks, and they have further fine-tuned a language model on these tasks. So here, one interesting idea that they have used is, so from a single data set, there are different varieties of tasks that can be generated. For example, if we take the SQuAD dataset, SQuAD is originally it's a extractive question answering dataset. So we have a passage, a paragraph, and there's a question, and there's a specific span in the paragraph which is the answer to that question. So it's an extractive question answering dataset. So now other tasks can also be generated from this. For example, query generation. We already have the paragraph, maybe we can generate a query from that, or context generation, that we have the question, can we generate the context for that. So just from the SQuAD data set, we can have multiple different tasks that can be created from it, and using this idea they were able to generate this huge number of tasks. Again, like we saw in the previous slides, here there's a distinction between which tasks appear in the training data set versus the ones in the held out task. So they are disjoint. There's no common tasks common tasks which appear both in training as well as held out set. So the authors of this paper, they also tried various data formats when fine tuning. So one way is your instruction tuning. So one way is when you're instruction tuning, you provide no examples. Just you ask that you have a question, which is, can you write a whole haiku in a single tweet? And you simply ask the question, answer the following yes or no question. So that's it. Or you can do is you can give examples. You have another question that you provide as an example to the language model, and then you ask the intended question. Another thing that you can try is using chain of thought prompting. So you can ask the language model to reason step by step. And here also there are two variations. You can give examples. You can simply ask the question without any example. So there are like 4 different like variations in the data format. So this is also like can be useful, and this technique was also discussed in the paper. If you look at the results, uh, first let's start from the topmost results. Here we can see that if we increase the model size and as well as if we increase the number of fine-tuning tasks, we see that the performance of the language model increases, improves. So if we look at the first graph, here each of the lines indicate a fixed number of tasks. Okay, and we see as the number of tasks are increasing, the lines are also ascending in the graph. So here, this is also indicative that with a higher number of tasks, the performance increases. Also now along the x-axis, we see the number of parameters of the model. So here also, if we increase the parameters of the model, we also see that there's this increasing trend. So the performance is increasing with higher number of model parameters, higher model size, better performance. In the second graph, again, here if we see along the x-axis, now we have the number of fine-tuning tasks. And here we have 3 models. We have an 8 billion model, we have 62 billion, and we have 540 billion parameter models. And we see that if we increase the model size, again, we see that the graphs are above the previous graphs. So there's an increase in performance, and also as we're increasing the number of tasks, the performance is increasing. So overall, the key takeaway is like when you increase the model size, when you increase the number of fine-tuning parameters, the performance increases. And like so, we are till now we're only focusing on like the improvement in performance. Does this come at a cost? Like, do we have to bear a lot of like compute or not? So here we compare the amount of compute that was required for pre-training versus that which was required for fine-tuning. We see that it's simply like 0.2%, 0.6%, 1.6%, which is like which is very, very less compared to. So the compute for fine-tuning is very, very less compared to what was required for the pre-training. And so here the authors have also tried to experiment across different varieties of tasks. Tasks with different architectures, encoder, decoder model, decoder only model, and also with different pre-training objectives. So we have span corruption, which is the pre-training objective for T5 models, for PALM models, which is a decoder only model. Their causal causal language modeling is the pre-training objective. So like that, across different varieties of language models, the authors have tried to see if the results are generalizable. So if we look at this big table over here, now if we look at the results, the difference in results between the base model and the fine-tuned version of the model, we see that there is an increment in performance which is written in this blue numbers, we can see. So all these blue numbers indicate that after fine-tuning the language model, we observe that the performance of the language model has become better. So the previous approach that we spoke about, there the instruction tuning data set was mainly mainly consisted of human written instructions. So that becomes very tedious when there's a human in the loop, like creating and writing instructions. It becomes very tedious and it becomes difficult to scale it beyond a certain point. So for that, there has been research which has explored automated ways of generating like instruction tuning data sets. And one important work in this area is that of self-instruct. So in this slide, we have the overview of the technique that they follow. So they start with a number of seed tasks. So there are 175 seed tasks. They have one instruction and one instance per task. This is human written initially. Then there's a task pool where they sample a number of instructions and they pass it to the language model, which in this case is GPT-3. And from that, they generate instructions, and there's a few details that we'll cover in the next few slides, but they create the instruction. That is one important step. Once you have the instruction, so the LLM creates the instruction, and once you have the instruction, you make the LLM itself generate instances like input output pairs, and then there's a filtering step involved, and if it's a valid reasonable instruction input output example that was generated, then it is added to the task pool, and like that the cycle goes on. So one of the steps that we saw was instruction generation. So for instruction generation, what is done is, from the initial pool, so we have 175 seed tasks. From the seed task, 8 tasks are sampled. Okay, and in this 8 tasks, 6 tasks are human written and 2 are generated by the language model. And like that, we pass the instructions for those existing tasks. So these would serve as examples. And based on this, we want the language model to generate new instructions. So these are the 8 tasks which were sampled, randomly sampled from the pool of seed tasks. And with this, new instructions will be generated. Now, once an instruction is generated, next we want to identify whether the task that corresponds to the instruction, is that a classification task or non-classification task. I'll mention the reason in some time for this distinction. So how do we do that? We prompt the language model again. So here we are doing few shot prompting. We prompt the language model with examples so given this is the task instruction, we need to, is this a classification task? Yes or no? So for example, you can describe a task with the instruction, given my personality and the job, tell me if I would be suitable. So the answer of this is yes, you can be suitable, you cannot be suitable. So there's a finite output space, and this is indeed a classification task. Another example is, give me an example of a time when you had to use your sense of humor. So this is not a classification task, this is a quite open-ended task, so this is not a classification task. So we are giving the language model examples which illustrate that given an instruction, the language model needs to predict whether the task is classification or not. And then finally, given all these examples, we pass to the language model the instruction for the target task, and it predicts whether it is or not. Till now, in step 1, we created the instruction. Step 2, we found out whether the task is a classification task or not. Now, the next step is, for classification tasks, there's a separate way in which we'll be generating the input and output, and for non-classification tasks, we'll be doing it in a separate way. This is because the authors of the paper saw that for classification tasks, since there's an finite output space, the language model gives importance to the more popular output labels. And as a result, in the final data set, the representation of examples across all the labels is not even. So we want like more or less equal number of examples across all the class labels that are present in the output space for the classification task. And for that, what the authors do is they propose this approach called output first approach for instance generation in case of classification task. So here they give the classification task definition, they give the class labels, and based on that, they ask the language model to generate an input that corresponds to the class level. So they're giving for example, they're giving the task label, which is the output label, and then they're asking the language model to generate the input or the sentence. And like that, finally, for the target task, the language model needs to perform this similar response the language model needs to generate. So these are all examples of few-shot prompting, where we are showing the language model. So this is the behavior I want the language model to follow. We are first showing the language model via the examples. Again, now if we talk about non-classification tasks, they're following the much more intuitive way that you give the task, then you ask the language model to first generate the input and then the output. So this is simple. And then there's also a filtering mechanism where we see that the new instruction that is generated should be different from the instructions that are already present in the task pool. So they have used Rougeal similarity score, and they have seen that Rougeal similarity score between the new instruction and the existing instruction should be less than 0.7. Only then the instruction will be included in the task pool. Second is keywords such as image, picture, graph. Instructions which contain such keywords will be excluded because the language model do not have the capacity to handle such inputs. Another is, now we have generated an instruction. At the time of instance generation, say we come across duplicate instances, we remove them, or for example, we come across instances where the input is same but the output is different. These are also removed. And finally, there's a heuristic based filtering where, say, so there's a constraint on the length of the instruction. So the instruction should not be too long or too short. And based on this also, filtering happens. So these are some examples of like data that was generated using this mechanism. So we can look at the last example. So here the instruction that was generated by the language model is write a story with 3 characters, a person, an animal, and an object. Then again, the input was also generated by the language model. So here we have a person named John, who's a programmer, an animal, a dog, an object, a laptop. And based on that, a story was again generated by the language model. So this is also like quite reasonable, valid data instance that was generated by the language model in an automatic way without any human in the loop. So there are other examples. You can pause the video and take a look at them. Nice survey paper, instruction tuning for large language models. Like I would encourage the students to read this paper if they're interested. And here in this slide, all the lists of various instruction tuning data sets are present. So in today's lecture, we discussed about instruction tuning, which is a technique via which we teach the language models to follow instructions. There are other techniques such as reinforcement learning from human feedback, which is RLHF, which further improves upon instruction tuning, and it helps the language model to better align with human objectives and preferences, so this topic would also be taken up in the upcoming weeks. Along with that, another point is when we spoke about instruction fine-tuning, we were mainly talking about that we are fully fine-tuning the language model. So the entire model is getting updated. So this is compute intensive, takes up a lot of memory. So there are much more efficient strategies present, that is PEFT, parameter efficient fine-tuning. So those strategies will also be covered in the upcoming lectures. So that's it from my end for today. Thank you for listening, and happy learning.